Good morning, all. Uh, we have just completed the first midterm exam. I believe while you are preparing yourself uh, for the midterm exam, you refresh your um, control subjects. And I believe the next part, which we are going to complete the course until the end of the semester, your information is is better be understood, or it's classified in a special manner. But one thing we know that in control system we have two major parts. One of them is the system. The other one, what we are doing for this system. Actuator and controller. Actuator is the one which you are not going to design. Actually, it's already there. However, the controller is the one, your responsibility to design it. It could be a constant value, proportional. It could be an integral, taking the taking the integral of the error, and also taking the derivative of the error. So it continues like this. Now today we are going to work on. We are not going to continue on stability. I remember we have completed the stability point, but if I continue further, I am going to give you. We all know that Routh-Hurwitz criterion is telling us that whether the system is stable or not. The first column, that one, follow my cursor, please. That one is your delta, which is the denominator of your transfer function, and this is the first column. If any change occurs in the first column, that means you have got, for each change, you have got one pole which is located in the right hand side of the S plane. That means unstable. So you are going to use the Routh's criterion, and that's if delta has got s to power 6, for example, for this part. This is the condition given the stability. You don't have to memorize that. It's already over there. And the location of the poles, that means we have 5 poles here. All of them are located in the left-hand side. So this system is stable. And also we have solved this one. You remember that. We are going to obtain the transfer function first, and then the transfer function denominators, in other words, characteristic equation is solved, and then you write down, if you look at here, s square is 1, and then 2s is 2 here, the constant of it, and the s to power, so s square, sorry, s to power 3 is 1. I'm sorry. S square is 1 here. The other one is 24. Multiply 1 to 2 minus 24 divided by 1, then you obtain minus 22. So one change in the sign telling us that there is one pole in the right hand side, and also another change occurs here. So there are two poles. So the system is not stable. System is not stable. But if you want to find the poles, that's I put it deliberately in order to show you easily you can obtain the poles. Don't worry about obtaining the poles in your engineering life. In your engineering life, or during examination, we are not going to allow you to use MATLAB or computers like this. It's impossible to provide you quality PCs. If any error occurs in the PC, so we cannot compensate that loss. You understand? That's why we do not conduct that examination in a computer room. Anyway, so if you write num is 1, then is 1 1 2 23. Let's go back. Sorry. So this is the transfer function. Num is 1, then is 1 1 2, then 24. Nerede o? Here. 1 1 2 24. There's always space here. Don't forget that dot comma here. Then if you write system transfer function num, then system feedback is going to get the system. And then if you write pole system, it's going to give you the poles. So you can see that one pole in -3, but the other poles are complex. However, the sign of the moment. If you look at the sign of that one, which is positive, that means our pole is located, one of them is somewhere there, the other one is somewhere there. That is sigma, and that one is imaginary. So this is S-plane, and the poles are located 2.6 imaginary part, and the real part is 1. Okay, that means unstable. This part is unstable part. Okay, so let's continue. We already have solved that one, and we have seen that K is also decisive. Later we have seen that increasing K is good for us. Increasing K is going to reduce the steady state error and things like this. However, it's also then might be dangerous to put ourselves in unstable region. You can see that. Sorry. I think I have solved that one on pad, and I have shown you that K was, just a moment. K between 0 and 8. We have already shown to you. I remember that on tablet. And also I've shown this one on tablet, and we have proved that the K should be higher than 0, but lower than 14 divided by 9. I have already solved that one too. It's already in your record. Now, before starting this one, which we have already started that, however, I would like to ask you one question. One question about stability. if delta is equal to s to power 3 plus 2s squared plus s plus 2, which we are going to write delta is the denominator of the transfer function, is this one. If you use the Raoult's criterion, s to power 3, s squared, s1, s0. So this is 1, 1. That's 2, 2. So what are you going to do? Two times 1 minus 2 times 1, which is equal to 0. So if you have a 0 here, what are you going to do? Is there anyone who proposed something to this, on this, among you? What you are going to write here, instead of 0, you are going to write epsilon. Then if you put epsilon here, epsilon times 2 minus 0 divided by epsilon, this becomes 2. So this system is stable. Okay, this is one example I would like to take your attention. If you have a 0 here, you are going to replace that 0 with epsilon. Okay, this is one example. Another example, if that one is clear, another example is even a bit difficult to understand. Is this one. Delta is equal to power 5 plus 2s to power 4 plus 24 s to power 3 plus 48 s squared minus 25 s minus 50 stupid minus 50 is equal to 0. So I prepare s to 5 s power to 4, s power to 3. What are we going to do? Put 1, 24, minus 25. That one here, 2, 48. Bir dakika. Yanlış ya. Ha, yok, doğru. Minus 50. What are you going to find this one? 2 times 24 minus 48, which is 0. What about that one? 2 times 25 minus 50, which is 0 too. If we have two zeros together, what are we going to do? What are we going to do? Is there anyone who suggests anything? Now, what you do actually, you take this line, which is PS. This line is equal to 2 to power s power 4 plus 48 s square, 48 s square plus değil minus, aferin bana, minus 50. Minus 50. So this is auxiliary. This one is auxiliary polynomial. It's called auxiliary polynomial. Polynomial. Okay. So what you are going to do, you are going to get delta P, delta S obtain first. Then you are going to obtain, if you get the derivative of that one is 8. I get the derivative of this one with respect to S. 8 S to power 3 plus 92 2 kere 8 16, 2 kere 8 90, 96, sorry, 96 S. So instead of that one, you replace it with this one. You instead of that one, you are going to write that one. So I continue with red. You put 8 here. Instead of that one, you put 96 over here. So instead of zeros, you write that one. So if you continue in that manner, you can continue s square, which is then s to power 1 and s to power 0. That is equal to 24, this one. Kırmızıyla devam edeyim ki anlayın değişiklikten sonra olduğunu. 24 minus 50. Kitaptan bakıyorum. Zero minus 50. So if you look at the first column of this one, is system is stable or not? Is this system stable or not? This is the first question. Who is going to answer? We have only 11 students in our classroom. It is rather sad. And those 11 students, nobody answered that question. I expect this system, whether this system is stable or not. Yusuf, Yunus, Raid, Muhammed, Mahmud, Halil, Hussein, Hamza, Ali Umut, Ahmed, Abdurrahman, come on. Not stable, but I'm not sure. Thank you. Thank you. At least we have got Hüseyin cevapladı değil mi? Yeah, Hüseyin Mahir. Of course, you should be sure. The answer is this. If there is any change occur between those values, here you can see that, follow my cursor. If any change occurs here, that means that change reflects that system is unstable and also tells you how many poles are in the right hand side. Here we have only one change. Thank you, Hussein. It is unstable. And one pole is in the right hand side. One pole only. You already learned how to calculate, how to obtain those poles. Geri gideceğim. I'm going to come back. You remember, it's S to 5. How many poles do we have? Çocuklar, transfer function, bakın, transfer function, TF, transfer function, is equal to something like this. A function here, function zeros, is giving you zeros. Kalemle kullanayım, daha hızlı yazıyorum. Zeros, but that one is delta. So that is delta. Now I'm asking you, how many poles your system have? Five poles. 1, 2, 3, 4, 5. You have 5 poles. How do you find those 5 poles? You can't, unless you employ that unless you employ that statement in MATLAB. You are going to write the numerator and denominator, 5, you have the constants here. Then if you write here, it's going to give you 5 poles. Bunu unutmayın. Don't forget that. It is important. In any polynomial, if you want to find the poles or if you find the roots, you are going to use that statement. I deliberately brought it here. It's another book's material, that one. Anyway, so we have seen that if we have problems with 1, 0 in first column, we use epsilon. If we have 0 in the first column and another 0 in the second column, which that means we are in trouble, then we are going to get the derivative of the one before part. We are going to get the derivative of this one and put this one instead of zeros. I did it. Now we also have completed that part, but I would like to emphasize this. So follow me carefully. What we covered we covered completely this topic, but please follow me. I also gave you all the details on iPad. I remember that. So you complained about my camera since it's not recording, you said, so I put it in iPad. So that reduced my speed. However, what I would like to be sure that you learn something basics, fundamental theories of the control. You should learn the basics. That's very important. Okay. Now let's continue. What's the main control system equation? So I'm going to write here on top of this one. The control system is going to be something like this. Something like this. There is something we require, which is RS. Then we compare that one with the result. So this one is plus, that one is minus. That one is error. Error. And now we design a controller, GC controller. Then, of course, actuator and system. Then you output. This is actuator. That one is system. And that one is our output. Output is compared to this one. So the main objective of the control theory is that part. That part. That part. GC. This is your task to define that one. It could be proportional, it could be derivative, it could be integral, or combination of those. Okay. So what we have seen here, the controller actually, control input is E, the output is U. So control output, that is the controller. So that one is U, that one is E in time domain. Temiz bir sayfaya yazacağım çocuklar. Anlamanızı istiyorum. Bu benim için önemli. That's very important for me. So that is the typical control system. you are comparing. That's minus, that's plus, and this is your in time domain. This is RT in time domain. The difference between reality, you have GC here, you have including actuator and everything system here. This is your output. Output is time domain, CT. So that one CT minus RT is ET, error time function. And that one here is UT. So controller actually, GC, has got input ET, error function, and the output is UT. According to error, your controller is providing another signal. This is what you should be, it should be understood. Okay, so for that case, error should be minimized. The main objective, of course, your system should be stable. Error should be minimized, or possibly, if it is possible, should be zero. So I come back to original course material. I'm just repeating what I have taught the week before examination. You remember that. If I feel that you understand those topics properly, then I would be very happy. Otherwise, I can also invite you to for extra teaching hours as well. Okay. So let's come back. Original slide. I don't know whether you would remember those or not, but I have already described it on the tablet. Now here, this one, that one is error, and that one is the error means input to the controller. That one is the output of the controller. If you have integral controller, I integral controller, actually error is integrated, although error becomes zero, but controller continues to provide a signal. That is what integral controller is all about. Integral controller always never forgets the error, since gets the integration of the error. So the cumulative error is known by the integral, and integral gets rid of the error. That's why the steady state error is reduced or possibly becomes zero with integral controller. Now if you come here, that is the proportional controller. Bakalım okuyalım şimdi. Ya proportional controller. Proportional controller ne demek? It's a constant. So the error, whatever the error is, actually controller transfer that error So that is also important, but that one is reduced to steady state error. Derivative is not driven here. Derivative means that you are getting the derivation of the controller. Sorry, you are getting the derivation of the error. Means that it's actually getting the derivation. So that means it's predict the value. For example, the maximum value of the error is predicted, is understood by the derivation. So derivation is predicts, understands what kind of change is going to occur in the future, and then it takes extra measures. Okay, so these are the inputs of the actuator, and these are the outputs. I have already derived those equations. So the transfer function of this one is known, and we have already derived that error over Rs is equal to, of course, error means Rs minus Cs. Cs is output over Rs. That means 1 over Cs over Rs. That means Cs over Rs here is obvious. That is simple. This equation is this. This is 1 minus so result is this 1 plus GS. So this is the error function then is multiplying with Rs. If that one is step, if Rs is step, that means 1 over S. Never forget that. Then if you put here 1 over S, you obtain this one. You already know that the steady state error, which is called ESS, which is a time function, by the way, is equal to limit time goes to infinite, and according to Laplace theorems, if time goes to 0, you are going to multiply that function with S, and S goes to 0. That's the function. When then we obtain that the error is 1 over 1 plus K. This is the error. Okay. So that reflects how important to increase the proportionality constant. K is the proportionality constant, so we have to increase K as much as possible. But we are going to see in the future that you have limits. You can't increase the K as much as you already have seen in stability problems, in route tables and things like this. This is another problem. If this is that is the first order system. If you add, instead of K, if you use integral control, what's going to happen? We have already proved that the error is going to be not this one. The error is, we have already proved that error is going to be 0. So one result. Listen carefully. One result. If you use proportional constant here, şunu bir sileyim, kafanız karışmasın. If you use a proportional constant here, that error is equal to this. Of course, K is high is nice, but it's not 0. But instead of that, if you use integral controller, then error becomes 0. I have already proved that one to you the week before on the pad. However, another point is important. the disturbance effect should be reduced. We have already seen that we use superposition theorem, and that means in order to evaluate the effect of the disturbance, we have only disturbance and there is no input for RS. Then when you solve this one, so this is a kind of line, and this is the output, and that is feedback. This is feedback. So when you solve it, this is output and this is feedback, G over G plus 1G. You are obtaining CS over DS is equal to this. Sorry, follow my cursor. I have already shown that one. Since C is equal E, there is no R here, of course, then it's equal minus CS over DS. So CS over DS is actually ES. So multiply with DS is giving you ES. So steady state error, I repeat, that's important. We are now looking for steady state error. Then when you sort it out, limit goes to S to 0, and then putting what did I put as a DS? What did I put? Is it a ramp input? What's that one? 1 over S gördün mü? As long as you see 1 over S, that means step. This is a step input. So multiply with step input, you obtain ES. Of course, you have to multiply with S. Then you obtain that your error, steady state error, is equal disturbance over Kp. So this problem reflects that increasing Kp is actually reducing the, I'm sorry, increasing Kp here is actually reducing the disturbance of the error. This is the error caused by the disturbance, okay? If that one is clear, I'm going to move that one. What is the difference between this one and the one before? The one before is this. The one before is this. There's only Kp here. For that one, we have an integral controller is added. An integral controller is added to this one. You can see that Kp plus 1 plus an integral controller. And I have already proved that when you solve this system, it's going to obtain that this one is going to be equal to 0. This is another proof that if your system is a second order, that one is a second order system, the disturbance effect is diminished, is even disappeared by the integral controller. That is also another proof that integral controller always deals with the steady state error. If that one is settled down, then we come to this kind of example. What's going to evaluate that one? We have already seen that when you use only integral controller, your system becomes unstable. So I always put those red ones, my notes to you. So you write here and see that your system is going to become unstable. You are going to solve this one again. You are going to put You are going to put that one is 0, and then this is only input, this is output, and that one is feedback. This one is a feedback line. Of course, it's a negative feedback. This negative sign involving here. Okay. So when you solve it, you are going to see that it's going to be unstable. So proportional plus integral is important. You are not going to use integral only for steady state. This is another example. We also have, as far as I can remember, we also have discussed that one. If you have a system like this, the inertia term only, there is no damping. Damping means resistance and things like this. This one. So if you multiply with this one, your solution is this. This is your solution. If you look at your inverse Laplace table, you are going to see that this is a cosine function or sine function, doesn't matter. I never memorized those, but this, as long as you obtain square here and kp here, so it's a sinusoidal function, and you can see that this is the waveform. That's the waveform. We are not happy about those. Now, if I ask you, if a system like this, where does your poles are located? If you answer that question, that means you are coming with me. We are moving together. If you cannot answer this question, so you have to consider your knowledge, understanding, whatever it is. I repeat my question. We have 16 students in our classroom right now. So I repeat my question. Can you understand the location of the poles of the transfer function? Can you obtain the location of the poles? Very simple. Since this one is delta is equal to gs square plus kp eşittir 0. So that means gs square is equal to minus kp. Hatta şöyle yazayım. S square is equal to kp minus j. So S1 is equal plus and minus so the poles are located. Who is going to interpret that one? Poles are located where? Poles are located here. Başka renkle çizeyim. One of the pole is located here. The other one is located there. So your poles are located j omega axis. You remember that if poles are located j omega axis, you are going to get sinusoidal output. However, for the same problem, if we add PD controller here, PD controller, sorry, PD controller, we are going to obtain this transfer function, and then it is seen that characteristic equation roots are in the left hand side of the S-plane, and the step response is stable. For that one, for this example, it was continuous oscillation, which we are not happy about that one. However, for that one, this is a for step response. That one is step response too. That one is step response too. You can see that. Continuous. However, for this one, it's a nice waveform. Of course, the overshoot and things like this can be considered. And that is the bir dakika zaten yapmışım. KP plus KDS. Aynı şey. Ama bir dakika pardon. Bu farklı. It's a second order system. Do you remember? Have we sorted out that one before? I think we did. This is our last one. Size yapıvereyim bunu. Yaptım mı daha evvel bilmiyorum ama beraber ondan sonra da ara vereceğim. Güzel bir ara yapacağız. We are going to take a break. Now system is this. Sorry, there's a disturbance here. second order system, output, compared. We have two inputs. One of them is major input, main input. The other one is a disturbance. That is equal Ki plus KDS. Öyle değil mi? Bir bakalım gene. Error de yokmuş değil mi? Neyse ben buraya error koydum. Bir dakika ya, bir önceki zaten aynısı değil mi ya? Yok, aynısı değil. Tamam. Ben kendi örneğimi yapacağım size. I'm going to solve it for you. Evet. That is the system. Amma çirkin yazmışım. Neyse artık. CS. Now, so what's happening actually? For error for this is yes. Yes. Error for TDS is asked. So what are we going to do? We are going to form this feedback line. So TDS over CS is equal times bu KP olacaktı. Times KP plus KDS. D'yi kullanmayayım böyle. Disturbance ile karışabilir. Şimdi bunu çözersek bu bir bölü S GS plus B plus KP plus KDS. O da eşittir. O da eşittir. Ben buraya sığdıramayacağım. Şunu sileyim. Şimdi burada there is something strange. If I were in the classroom, I was not recording those. So you were taking those notes by your, your notebook. But now it's already recorded. Evet. Bu da eşittir. Bunu da kırmızı ile yazayım da son ne olduğu çıksın ortaya. Is equal to 1 bölü, evet, kalemi alalım elimize. GS square plus B plus KD S plus KP. Bir kontrol edin çocuklar. You check it up. First, that one, cursörle göstereyim. That one is our transfer function. So for TDS, so TDS over CS is equal to this. Aynı zamanda TDS over CS is equal to since ES is equal CS, so ES, bunu da buraya gene kırmızıyla mı yazayım? Kırmızıyla yazayım. ES is equal minus CS. Buradan you can obtain the error function and you can solve it. You understand? You have to think about those. You have to spend time on this. Control is a complex business. You cannot learn it. Whatever the teacher is telling you, you have to make those practice by yourself. You have to buy books, or download books. There are solved problems in it. So if you want to be a good control engineer, which you should be, the future is in electrical and electronic engineering. Whatever the electric and electronic engineering occurs, there is always a control in it. Okay, let's take a break. So I'm going to continue on error business. Although the method I have given is already established, you can already could obtain the error easily by taking limit SES is equal to the steady state error. Okay, we'd better take a break. Şu sayfayı temizliyorum. Nasılsa kayda geçti. Kaçta buluşalım? Evet. Ten 20. Yok, 25. 10:25. Bir kahve için bir şey yapın, bir hareket edin. Tamam mı? Break. Okay. Hello again. That is the examination question, midterm exam question in earlier. It was 2016. So you'd better test yourself. If I could have asked those questions, whether you could have done it or not. These are the examination questions. All right. Try to solve it by yourself. Yes, in order to draw a curve, so you are going to use those statements. I have already passed that point. Now, the steady state error. I believe you can solve steady state errors by the method which have covered. However, your book is also emphasized on this one and classify the system with type. Type means that if you look at the control systems uh, GS, you can see that it's not a feedback, it's not a transfer function, just system. If you look at the system, you can see that there's a constant here and the zeros. You have zeros here. I don't know how many, depends your systems, but the number of zeros is m. And also you have poles. Number of poles are p poles. But if those are multiplied with a constant s, in that case, your system is defined with the order of the n. If n is equal 0, is called type 1, sorry, type 0. If n equal to 0, is called type 0. That means there is no s actually. N is equal 1, which is s type 1. N equal to s square is a type 2. S power to 3 is s type 3. Okay, so that defines the type. That is the one you have already done it actually, which es over rs is equal rs minus cs. That's the one we have obtained, and then we have derived that. You remember that ess is equal time goes to infinite limit et, which is equal to limit s goes to 0 ses. Then it's equal to limit s goes to 0 s over 1 plus gs times rs. Rs might be step. So this chapter is generalizing the error. So rs might be step, rs might be ramp, rs also might be parabolic. So Now, static position error. For static position error, it's a step input. Static position error. For example, theta, for example, x. And the constant is called Kp. They define error with the constants. In my teaching approach, I really do not appreciate their method, since you have already learned how to obtain the steady state error with this one. If Rs is equal to step, you are going to put 1 over S here. If Rs is ramp, you are going to put 1 over S squared, or 1 over, for parabolic, 1 over S to power 3. But they define it as static position error, and then, of course, classify with respect to type. For then what they say, you remember this equation here, S goes to 0, S over 1 plus GS times RS. This is a general equation. So if you come here, this is for step input, is equal to this one. Then the definition is this: Kp is equal limit S goes to 0 GS. That, for example, type 0 system, it is K. For type 1 system, its error becomes 0. That is, I believe, easily you can do that without those rules. For velocity error, they call it. In that case, it's a ramp input. Ramp, if it is a ramp input, of course, 1 over S squared. When you multiply with 1 over S squared, then, of course, probably you might miss this one. So I'm going to help you to clarify that. That one here is equal to 1 over S plus SGS. Limit S goes to 0, that becomes 0. That's why they present it like this. Is it clear now? Since this one is equal to 1 over 1 plus, I'm talking about this equation, 1 plus GS 1 over S squared, they call it velocity error. That is new for you. That one. This one is a static position error, step response. That one is velocity error for ramp response. And then, of course, according to type of the system, bir temizleyeyim şurayı. According to type of the system, if type is a 0, your error becomes infinite, since there's S involving here. For type 1 system, your error becomes 1 over K. For type 2 and higher system is 0. And that is the response. Another one, third one, bir dakika bakın çocuklar. Kafanız karışmasın. Biraz evvel anlattıklarımın aynısı bu. Fakat burada kitabınız şimdi buna diyor ki, bu diyor static position error olsun diyor step response'a. 1 diyelim. Sonra ramp response geliyor. Bu da diyor static velocity error olsun diyor. Bu da 2. 2 diyelim. Sonra da parabolik veriyor. Buna da acceleration diyor. Şimdi acceleration, speed and position always derivative. Derivative of the position is speed. Derivative of the speed is acceleration. Tamam mı? 3. Bu da üçüncüsü. Bunu da aynı şekilde yazmış. They put s to power 3 here. Then when you analyze it, for type 0 and type 1 system, it becomes infinite. For type 2 system is equal 1 over k. For type 3 system is 0. So in order to simplify, in their mind, probably, in order to simplify this, you give that chart. That chart is easy. For step input, type 0, type 1, type 2 system, errors are clearly can be seen. For ramp input, it's infinite, and acceleration input is simple infinite. For type 1 system is 1 over k. For type 2 system is 1 over k. 0, 0, 1 over k. Of course, that's the error, steady state error is 0 for type 2 system here, and 0 for type 2 system is there too. Şuradan çıkıyor. Burada. When you solve it, when you solve this one, if you put 1 over s to power 3, which is a ramp input, then you are going to obtain it. You have to read those properly. You have to think about those. And if you don't understand that, you can write me. These are the questions you think about those. And that one also is you have to think about this. Okay. Now it is the steady state error business is over, stability is over, step response problem, particularly the settling time, rise time, maximum motion is over. Now we are going to start another very important topic. We are getting in design. We are going to design a control system. So PID, these are the three parameters, but how could we calculate those is important. We are going to use Roots-Lucas method. Roots-Lucas method. Evet, bir şey daha yükleyeceğim şimdi. Analysis and design of control system by Routh-Lucas method. Now follow me carefully. You can easily obtain the transfer function of this one, which is equal to GS over 1 plus GSHS. Delta here is the transfer, the denominator of the transfer function, which is called characteristic equation. Now, what we are going to looking for, while the K parameter, the proportionality constant, is changing, what kind of change occurs in our system, or the trajectory of the poles. Poles are location of the poles, you know that. Poles could be real, could be complex, could be equal to each other, real. That's a critically damped case. Anyway, delta is 1 plus GSHS is equal to 0 is characteristic equation. Therefore, GSHS is equal minus 1. Look, that method, while we are students, or even the years later, since the computer methods to draw the trajectory of the poles are not developed yet at that time in the history, those curves are driven by hand. Thanks God that there is no need to do that. I remember it took weeks to describe how to draw those curves. But I'm going to teach the basics of drawing the curves since computer is going to draw your curves. But one thing is obvious, GSHS amplitude should be minus 1. In other words, GSHS amplitude should be 1, or GSHS should be minus 1. This is one point. So absolute value, the amplitude, as I told you before, should be 1. But the other one, angle, should be 180 degree or the odd order of those. Türkçe söyleyeceğim. GSHS'in şeysi, mutlak değeri 1 olacak. Açısı ise 180 derece ve onun tek katları olacak. I repeat in English. Absolute value should be 1 and the angle should be 180 degree and the odd orders of it. Tek sayı katları olacak. Şimdi geçelim. Bu elle çizim nasıl oluyor? That is for example a point and these are the poles and the total angle of those angle. Look, this angle, that angle, that angle, that angle, whatever the value, even zero, not only the poles, since GSHS angle of it, that means zeros also might be over there. Total angle should be 180 degree or the order of it. Ne bileyim 3 katı, 5 katı olabilir. Ama 360 olamaz. It can't be 380. Yani çift sayı katı olamaz. 180 derece ve katları olacak. Tek katlar olacak. Açılar böyle. Bakın açıları hep tanımlamış. Bunlar elle çizmek için anlatılan şeyler. These are the points to draw, but you have to know the rule. GS angle should be 180 degree. Şimdi in starting point, you have a system and you have a constant. That constant parameter is of course reflecting the proportionality constant. The GSHS is equal, you have some zeros, you have some poles. You know that. But you now multiply with K. However, delta is 1 plus GSHS, değil mi? Delta is equal 1 plus GSHS. 1 plus that one should be 0. Of course, if the pole is without satisfying those equations, that is wrong. So your poles and zeros should satisfy those equations. That means 1 plus k times zeros divided by poles should be 0. Şimdi 1 ile çarpalım bu iki tarafı. So S plus P1, S plus P2 times that one plus this also çarpıyorum. S P1, S plus P2, S Pn plus K times that one is equal to 0. Şimdi çocuklar burada beni iyi dinleyin. Hem Türkçe söyleyeceğim hem İngilizce söyleyeceğim. I'm going to tell in Turkish first, then I'm going to write in English. Şimdi bunun sıfır olması için K'nın iki değeri var. K sıfır ve K sonsuz. K sıfır iken burası zaten sıfır. Neresi sıfır olacak? K sıfır iken bu sıfır olacak. Yani zerolar sağlayacak. Buna karşılık K sonsuz iken buranın hiçbir önemi yok. Bu zaten sonsuz olmuş. Bunu yok etmenin tek çaresi var. Polların değeri. Yani S'in bir pol değerine gelmesi lazım ki sıfırla çarpılsın. Tamam mı? Onun için bakın I'm going to explain it in English now. This is the equation which is derived from this one. Okay? Delta. That also reflects delta. But for k is changing from 0 to infinite. If k is equal to 0, this term is already 0. So only in order to make this term 0, it should be one of the zeros. One of the poles. If one of the poles are 0, then equal to 0, then this equation is satisfied. I start k equals 0, the poles are defining. You can see that if k equals 0, roots of the characteristic equation are poles of the H. Only S equal poles satisfy the characteristic equation equals 0. So poles are satisfying. On the other hand, for k equal infinite, which means the zeros are satisfying, S equals 0, k equal infinite times or very near to infinite times 0 should be 0. Otherwise, it can't be 0. Okay. This means that the curve actually bakayım burada ne geldi? Evet, ben bir şey anlatmam gerekiyor benim size şimdi. That is the system. We are looking for Root-Locus method, which the GS is equal K, but K is variable. K is changing from 0 to infinite. Now, what kind of curve do you expect? Şimdi benle beraber gelin. This is the transfer function. That one is K, which is GC actually, controller. That is the system. That is output. That's input. This one is output. Okay. So this is plus, that one is minus. That one is error. We already know that. Now, K starting, changing to infinite. What's going to happen? Of course, the system equations are very important, but nevertheless, the location of the poles might be changing with the change of the, for starting K equals 0. K equals 0 means that you are starting with the pole. Just say that one pole is located, kırmızıya geçiyorum. One pole is located here, let's say. The other pole is located here. So that one is K equals 0 point. That one is K equals 0 point. As we proved that only the poles can satisfy it. When you increase the K, of course you cannot predict the curve, but when you increase the K, the curve is going to start moving and coming here at a point which is joint point, and then the curve is going to continue like this if system is second order. For a second order system, when K goes to infinite here and also here down there, K equal infinite, then there is no obvious zero. If there is no obvious zero, then the curves are going to be asymptotic, all right? So, for example, this one is K1. That one is also K1. K equal 1. That one, for example, K equal 5. Uydurarak söylüyorum. That one is equal K equal 5. Bu 10. Bu da 10. Tamam mı? Böyle sonsuza kadar. K değiştikçe, while K is changing, the curve is changing. Şimdi bir soru soracağım size. Why we use that one? Why we use that kind of trajectory? Why do we need those trajectories? I wish I could see your faces. Well, while when I see your faces, I can understand whether you are following me or not. But here it's up to you. You are responsible to yourself, not to me. I repeat my question. Ben bunu, neyse şu yukarıdaki dursun. Ona acıdığım için. Niye büyütemedim ki şeyi ben ya? Yazıyı büyütüyorsun da silgiyi büyütemiyorsun. Allah Allah. Bir dakika. Yok. Gezmiyor. Heh, sıkıldım. I draw another curve. Real points, imaginary points, and poles are located like this. One of the poles is here, the other one is here, -4, 0, and the other one is located here, 8, -8. So your journey is starting with k equals 0. Start with k equals 0, which are poles. So when you increase k, the curve is moving like this. These two poles couple, and then roots are approaching here in the middle of point. So this one is k infinite point. That one is k infinite. That one is, for example, that one was k equals 0. That one was k equals 0. But this also, this pole k equal infinite, it goes like this. So if you have a curve like this, I have a question now. If you answer this question, I would be very happy. Why do we use those curves? Where do we use? K in your control system, K might be 0, K might be 5, 8, or infinite. Which one do you like? Think about step response. I'm not sure whether you are thinking about this. Please think about this. Thinking, you see, in fourth year, I have been teaching the course called Science, Technology, and Ethics. Science is starting with thinking, observation, and evaluating, then experimental measurement and things like this comes follow. But thinking or positive rationalism in English, rasyonel düşünce in Turkish, yani mantıklı düşünce çok önemli. You always evaluate things around you. You have to criticize, of course. If you criticize me, I never bother. I enjoy, since I always evaluate whether that criticism is correct or not. If it is not, I just say that that student should be improved. That student's criticism is not correct. But if that criticism is correct, right, in my mind, then of course I change that attitude. So now we come here. Think about this curve. I explained in root locus, the computer is drawing that curve, but the curve is starting from k equals 0, the poles, actually, the poles, then moving. If there is no 0 in your system, the k equal origin. I don't want to use 0 again. It's misleading. This is origin. So it's that one pole is located in origin. The other one is not necessarily, by the way. For example, write the GS curve for this one. The curve is this. S kalemle yazayım. S plus 4 S plus 8 1. There is no 0 here. You understand? One pole is located in -4, one pole is located as -8, the other pole is located in origin. Now, there is a k here, by the way. K here. Now, k is increasing, symmetrical, starting journey from this, coming here. At this point, the two poles are equal. Zeta is equal to 1, so it's a critically damped case. So there is, when you increase k, perhaps you can obtain critically damped case. But what is the best one? The best one is that point. That point. So where, bunu siyahla çizeyim bunları. Hadi kendi rengiyle çizelim ya. Madem böyle yaptık. Omega D and the real, so S1, S2, most likely S3 is somewhere here. S3. So When you increase K, actually your poles are moving, and you are able to define the best K value for you. Burası tamam mı? Is it all right for you? K is changing. K is changing. Starting from 0 to infinite. You have infinite choices. Which K you are going to select? Of course, you are going to select zeta is equal to 0.67, somewhere there. That is the one you select. Zeta is defining the step response. For step response, this is time, this is function, step response. So step response for this case, for that value is somewhere there. Is nice. It's going to be nice. So it's going to be, the overshoot is going to be less, and the settling time should be short. So that's, you can design your system. Sigma also here. Your pole sigma plus a minus j omega d. S1, 2 is equal to. You are selecting the value of K. I have another question. Kara nokta olarak göstereceğim. Black point. What about that point? And this point? Is it important to know that K value here? I repeat, nobody is answering. Is it important to know the K value? What's the K value here? How could you find the K value here? If you increase the value of K, your system roots are moving to the right hand side of the S plane. This one is S plane. That one is S plane. So if you make K higher than those limits, your system becomes unstable. You may employ the Rauth-Lucas curve, for example. Is there any suggestion to obtain the K value over here? İçinizden bir teklifte bulunan olacak mı? Is there any, what's the K value here? Ben boşuna mı konuşuyorum acaba ya çocuklar? O noktadaki K'yi bulamaz mısınız? Bir teklif, koca sınıftan bir tane ya ben bu K'yi bulurum diyen yok mu? Abdurrahman, Ahmet, Ali Ümit, Umut, Hamen, Cemile Nur, Hamza Muhammed, Hilal Bassam, Hüseyin Mahir, Halil Hatim, Mahmut Ramadan, Muhammed Kamil, Omar Şuanki, Raid Hasuna, Tahir Muhammed, Yunus Emre Çelebi, Yusuf Selim. Among those students, which I believe they are already in our classroom, I'm not talking about those who haven't come here, but just half an hour ago, I talked about stability, or an hour ago, I talked about stability. And I also discussed how could you find the K value for stability limit. Yapacağım. Ben anlamadım. Yani çocuklar, önce Türkçe söyleyeceğim, sonra İngilizce. I'm going to first say in Turkish. Teknik üniversiteden beri öğrencilerimde şu özelliği görürüm. Çalışkan öğrenciler dahildir buna. Bir dersin bir konusu önemli, ciltli bir kitaptır. O konuyu öğrendiğimizi düşündüğümüz anda o cildi hemen kapatırız, kilitleriz. Beynimizin bir yerine yerleştirip açılmamak üzere yerleştiririz. Eğer o konuyla ilgili bir problemle karşılaşırsak o kitabı açar, o defteri açar, o çözeriz. Ama birden çok beynimize istiflenmiş derslerin bir arada getirdiği sentezden maalesef istediğim verimi alamadım bugüne kadar. Sentez çok önemli. Şimdi bakın biraz evvel Raut-Hurwitz kriteriyle şeyi inceledik. Stabiliteyi ve K'nın değerinin değişmesiyle sistemin stabil olmadığını da bazı durumlarda öğrendik. Şimdi yapacağım. So I come back to English. In normal education, I have observed that the students always consider courses as a notebook, which is binded, closed. When they learn it, if you ask a question about them, they open up that notebook in their brain, they think about that, solve it, and then close it again. Close it. But if you have a question which use more than 2-3 notebooks together, students couldn't be able to open up all those classers, all those files together and to synthesize it. Synthesizing control system is a kind of course to improve your mental, let's say, discussion ability or thinking ability. Therefore, you have to always consider and ask question, why do we learn this? What kind of use I'm going to use it? Where do I use it? For example, now the answer I expected you, sizden beklediğim cevap şuydu. We use Raut-Hurwitz criterion and we can obtain, since transfer function is already known here, is already given here, so I can find it. So I go back. Evet, bunu clean etmem lazım benim, mecburen. So I repeat, the journey of the poles are starting from K for poles which are K equals 0 points, and then while you are increasing K, your trajectory of the poles shifted, moves, and then, for example, come here. Of course, if you select the K value somewhere there, it's going to be very oscillatory. Bir tane seçeyim, ondan sonra geçeyim şeye. Burada bir pol seçtim. Yeşil renkli. Simetri de var. Öbürü de buralarda bir yerde. Buralarda bir yerde. Sonsuza doğru gidiyor K. Şimdi burada bakın. Bir kere şu açı çok büyüdü. Dolayısıyla step response'ı bunun böyle bir şey olacak. Daha da inecek. Böyle berbat bir şey olacak. Step response. Bunu ister miyiz biz? Do we like this one? Of course we don't like it. And also very near to the stability limit. Okay? So selection of the K value is obvious from this curve, and we can design our control system by looking at root locus. Şimdi şunu çözeceğim yalnız çocuklar. Şunu çözeceğim. Yani size K'nın hangi değerinde I'm going to find which K value system is going to be unstable. I'm going to find this. S plus 4, S plus 8. Evet, rengimiz black'ti. Çarpalım bakalım. S kare, S parantezine alıyorum. S kare artı 4S 8S daha 12S artı 4 kere 8 32. O da eşittir. S küp artı 12 S kare artı 32S. Şimdi bunun transfer fonksiyonu 32S. Transfer fonksiyonu şu. TF is equal K bölü S küp artı 12S kare artı 32S artı K. Şimdi buradan S küp 12 S kare S üzeri 1 S üzeri 0 0. S küp 1 32. Bir dakika K ne oldu? Artı K. Pardon. Artı K. Neyse. Şurada zaten bu. 12 S küp 1 12 bir de 32. 32. 12 K. Şimdi bu hesap makinesi çıkaracağım. Yo bir dakika. 12 32 çarpı yok olmaz. Şöyle yazalım ya. Daha kolay değil mi bu? 12 çarpı 32 eksi k bölü 12. Dolayısıyla 32 eksi k bölü 32. Değil mi? Doğru değil mi? You control it. Bununla çarptım. Bunu da bununla çarptım. 12 çarpı 32 eksi k. Hepsini 12'ye böldüm. Dolayısıyla 32 eksi k bölü 32. Bir dakika, eksi k bölü 12, pardon. Sorry. Sorry, I made a mistake. Burası 0. Burası that one times, sorry, follow my cursor please. That one times this one divided that one, which is equal to k. Which is equal to k. Şimdi 32 minus k over 12 büyüktür 0 olmak zorunda. So k over 12, k buraya aldım. K over 12 32. 32 ile 12'yi çarparsak, çarpalım şimdi. 384. 384 K 384 ile 0 arasında değişiyor. Demek ki orası 384'müş. Olduğu zaman artık uçuyor. Yani bizim grafiği hemen şuraya çizeyim. Grafiğimiz şöyleydi. Anlaşılması önemli çocuklar bu işin. Root locus üzerinde durduğum bir konudur. Böyleydi. Burada K demek ki K eşittir 384'müş. Eğer ya hata yapmadıysam hesaplamada K 384'müş. K 384'ten büyük olduğunda uçacak bu tarafa doğru. K çünkü artmaya devam ediyor. K increase. Yani olsa burada da bir kutup var. O da böyle bu tarafa doğru gidiyor. Diyelim buralarda bir yerde K'nın arttığı değerler. Sonsuza doğru gidiyor. Evet, anladınız herhalde. Seçeceğimiz pollar şurada olmalı. The best poles would be located somewhere there. So I come back to my original slide. Starting from very beginning, we now analyzing the root locus method. Our control system is this, where G and H might have zeros and poles, but transfer function is obviously 1 plus GSHS. 1 plus GSHS is delta, characteristic equation, and those delta should satisfy GSHS minus 1 and the angle 180 degree, total angle 180 degree. These are the figures I have shown you. So this is the GSHS, and the delta is equal 1 plus GSHS. Therefore, you write like this, and if you multiply both sides with zeros, you obtain this function. And this tells us that for k equals 0, this term is already 0. So poles are defined. The value of k, for you are starting your journey for k equals 0 with your poles. But when k increases, of course, the trajectory is going to change. But at the end of the journey, k varying between 0 and infinite, when k becomes infinite, then of course, if you put infinite here, only the zeros can satisfy this one to obtain the zero condition. Therefore, your journey will end up with zeros if you have zeros, by the way. If you do not have zeros, it becomes asymptotic. That's a typical control system. And the computer MATLAB is going to draw those curves. Whatever you are going to write root locus system, if you write the system equation, root locus system is going to draw those curves. And now we are starting with an example. This is a typical second order system. What would be the trajectory of the, the transfer function, of course, k is varying from 0 to infinite. And now if you draw the curve, you are going to obtain, of course, transfer function is obvious here. S square plus 2s plus k is the characteristic equation. Kafadan yaptım. S square çarp, follow my cursor, 1 plus gs, I'm sorry, 1 plus gh is the transfer function. So s square plus 2h, s square plus 2s plus k is your characteristic equation. You can see that transfer function is obtained as k over s square plus 2s over plus k. And then the gh is equal k 1 over s square plus 2s. So p is 1. You can see that. And that one is 102. Sorry, 120. You can see that. That term, GH. GH'i çiziyorsunuz çocuklar. Tepesi 1. Bu 1, 2, 0, 1, 2, 0. Then you write system transfer function PQ diyorsunuz. Buna P demiştik, buna Q demiştik. Root locus system dediğin zaman sana bu eğriyi çizecek. Bu eğriyi çizecek. Biraz buraya geri döneyim. Acık hızlı gittik. Şimdi tahtada yazılmadığı için çarçabuk öğrenilmediğini biliyorum. I know. If I write on the board, probably you will follow it. Now you have a second order system like this. So we have to. This is the transfer function of it, and we are looking for the poles of the. We know that delta is 1 plus gh, so 1 plus k times 1 over s2. Gh here is equal to k over 1 plus s squared plus 2s. So we draw the GH, by the way. Neden? Neden? Çünkü GH'in değeri 1 olmalı. Amplitude might be 1 and the angle 130 olmalı. Bu condition'ı satisfy eden grafikleri çıkarıyoruz. Of course bize şeyi çiziyor. Yani merak etmeyin. Transfer fonksiyonunu çiziyor. Bakın çizdiği grafik. Yani bunu tekrar edeyim. GH'i veriyoruz bakın. P1 dedik. Q'ya 1, 2, 0 dedik. 1, 2 yok 0. System transfer function PQ dedik. Yani transfer fonksiyonu kendisine buldurttuk. Tamam mı? Sonra root locus system dedik. Transfer fonksiyonu yani o kendisi alıyor. Biz elle yapmak zorunda kalmıyoruz. We don't have to calculate the transfer function of this one by hand. Of course, this one is very simple, but you are going to face with some complex systems. You don't have to. Computer is going to do that. You are going to write GH, and then you are going to say system transfer function. That means system is going to get the transfer function, and then of course you may see the transfer function as well if you want. Root locus system is going to give you this curve. This is your root locus curve. Şimdi bakın burada beni iyi dinleyin. Biraz evvel çizdiğim değerler. Şurası, incelteyim kalemimi. 5 punto yazmaya çalışıyor. Evet. 3 puntoya indim. Bir de kırmızıya geçelim. Şimdi burası bir tanesi k eşittir. Burası eksi k, burası 0. Origin. K eşittir 0 değeri. Bu da k eşittir 0 değeri. Şimdi grafik başlıyor. K'yı artırıyoruz. I increase K point by point. My curve is coming here. Burada bir K değeri var. O K değerinde critically damped oluyor. Ondan sonra da K infinite, bir K infinite de burada var. K infinite. One conclusion. System is always stable. System is always stable. The best value of K you select according to your step time. Şimdi settling time kaçtı? 4 bölü sigma'ydı. Demek ki if sigma is higher, is nice for you. This is one point. And also zeta 0.7 was good. So kaç dereceye karşılık geliyordu? Galiba 60 dereceye karşılık geliyordu. Unuttum şimdi ezbere söylemeyeyim. Kök 2 bölü 2 45 derecedir. Neyse uzatmayalım. So these are our best operating points. That one here. And these two poles are our best operating points. So that is omega d, that is minus omega d, value, and that one is sigma. Okay. So system is always stable. The final example I'm going to show you before completing my course is that one. We have 3 poles here. So if you write GH. Burada G kaç? Yazalım. Bu G bu. Bu G bu. G P diyelim buna. P 1 ya da 0 0 3 tane var. 1 Q yerine de S küp 1 kaç çıkıyor bu? Bir dakika. S küp 1. 2S buradan gelir. 1S de buradan gelir. 3S 3 S kare. Ondan sonra başka 2 böyle gelir. Bir de 0 koyarsın. Noktalı virgülleri unutun da benim gibi ondan sonra merakla bekleyin niye çalışmıyor diye. Demek ki bu 3 tane 0, 4 tane 0 var burada. 0, 0, 0, 1. Bir de yazsa kabul eder. Understand that one. Sonra system yazıyorsun. System. Sonra da root locus diyorsun. PQ diyorsun. Bak ne çiziyor sana. Bunu çiziyor. Draws that curve. Draws that curve. That pole bu S equal 0 S equal minus 1 bunlar. Ondan sonra S equal minus 2 var bir de. Bu these two couples produce that curve. So starting from this k equals 0 values bunlar. Bu k equal 0 value. Bu da k equals 0 value. Bu da k equals 0 values. So when you increase k, your curve is going to increase like this. Hop. When k reach 6, beyond that it becomes, and that is the value. K infinite. It's already given here. Biraz küçültürsem göreceksiniz. These are k infinite values. That's the one. K infinite values. That's the end of my lecture. Most likely, Said Mohammed is going to, I don't know whether he's in the classroom or not. He hasn't in classroom yet. Don't move. I'm going to take the attendance list. I want to be sure that I put our attendance list attached in my lecture notes. Yusuf Selim is the last name. Yunus Emre, Tahir Mehmet, Raid, Omar, Muhammed, Kamil, Mahmut Ramadan, Halil Hatim, Hüseyin Mahir, Hilal Başan, Hamza Muhammed, Danish Münir, Cemile Nur, Ahmet Walsh, Ali Umut Terzi, Ahmet O, Abdurrahman Efe Kork. Just a moment. Don't leave. Don't leave. I'm not sure about this list. Abdurrahman mı first name? Kontrol edeceğim. Abdurrahman Efe. Evet, tamam. Korkmaz herhalde ya da kork. Tamam. Tamam. So Yusuf Selim var mı bakayım? Bir dakika. Bir dakika. Tamam. Yusuf Selim de var. Peki. Çocuklar, we are going to take a break. Most likely Muhammad Seyit will be joining or has already joined. I don't know. Let's have a look. He hasn't. Yes, he's already.
Buradayım hocam.
Seyit,
Buyurun hocam.
hiç ara vermedik. Çok yani yorgunlar. İstersen bir 5 dakika veya 10 dakika ara ver. Sonra
Tamam.
yap. Olur mu?
Tamam, 10 dakika mola verelim o zaman.
Tamam. 10 minutes break. Okay? Don't leave. It's important. Okay? Good luck all. Bye bye.
Hello, everybody. Does everyone hear? We're gonna start now. Yep. Let's start, guys. Yeah, so everyone can see my screen now. Okay. So today we're gonna see the unit step response. Do you know unit step response? What is unit step response, guys? Any idea? All right. Okay, let's take a look. The step response of a system is the we can say to the unit step input is called the unit step response, the response of our system, right? So now we're gonna see how we're gonna visualize this response in MATLAB. First, we have our system, and in our time frame, let's say t equals to 0 to 0 0.01, and make it 5, right? So we have a feedback k values, and this is our feedback 0.2. Now we have a system. Now we're going to define as our system. We have feedback, all right? We have feedback with 0 0.12, 0 0.3, 0 0.4, and 0 0.5. And now we're gonna try to visualize this step response with these feedbacks. So first, let's say for n equals 5. All right, for our feedbacks from 1 to 5, let's define our numerator 1 equals to create a system. Right, we define our numerator and denominator. Then one, let's say, the same. System one, let's say, this is our first system. Now we're gonna make a loop, feedback loop. So first system, we define it as, let's say, transfer function of numerator 1 and denominator 1. All right. So you remember how to take a transfer function of a system, right? We did it in a previous labs. You have defined your numerator here, all right? You define your denominator, and then you just write system for our system 1 is just equals to transfer tf. This function is create a transfer function, and in a parentheses you need to write your numerator and denominator, right? So let's go to our system 2. Our system 2, let's say, equals to for feedback function kn. All right. So our system 2 is our feedback. Now let's go our third system. This is our third system. We can define our numerator and denominator. Third one, right? 0 and 1. Let's see. And then our system 3, say it's equals to. Now, how we're going to take transfer function? Just as same before. TF function, you write to your numerator and denominator. Num3, denominator 3. All right, guys? So now we're going to define our feedback. System1, let's say, equals to feedback. This feedback function, as we talked about it before, define our feedback, and then in your open parentheses, and you write your feedback function, which is in our system. We're going to use system1 and system2. So the system1 we defined here, and the system2 here will be our feedbacks. For the system2, say we connect them in series, all right? We can write the series function, and it will define our systems in series. We can write system1 and system3. All right, just this, if your system is connected in series, you can connect it with this series function, right? Okay, let's go to our feedback again. Now, our final system, let's say, is feedback of our system2. Right. All right. So now we're going to define our y. So with this function, we're going to turn our feedback values that we said we want to see the response of 0.1, 0.2, 3, 4, and 5. We want to see them one by one. So with this function, we're going to visualize all of them. So when you complete it, you just write equal, and you write step function. So we need to step response. And of course, you need to write your system inside parentheses and t for the time, right? And you have a for loop. So at the end of your function you write, you need to close that for loop. So we're going to add end. At the end, now we're going to start to plot our step response. So the time and our y value. Yeah. So after that, we're going to write our grid. And we can add title to our plot, that you can just write, let's say, unit step response. We can write it. Unit step response. You can write whatever you want for that plot name. And then we're going to write for the X label, for our X-axis, that which it represents time for us. So you can write T in second, then you can explain it. For the Y label, we're gonna see our output, so you can just write it outputs, right? So now this is our function. We have a system, we define it here, we connect them in series, and we connect with our feedbacks, and then we want to turn this feedback values, and we're gonna see the step response. Let's run the section. Yeah. So as you can see, this is our unit step function, the unit step response. Let's close this one. Yeah, so this is our unit step response with our feedbacks from 1 to 5. Any question, guys? How we get the step response from our systems with the feedback values? All clear? Clear, guys? Yep. So, okay then, you can write yes or no, guys, if you hear me. Any question till here for the unit step response? All right, good. Okay, let's go to do our second. Okay. So now let's clear our output. Let's start a new one. For this, we're gonna visualize with the labels right now. Let's define, we have our A value. So now we're gonna define our with zeta. You know what is zeta, guys? We're gonna see how our system response will represent to change in zeta. Zeta is the damping ratio. Zeta gives the level of the damping. All right, let's start with A equals to, let's define a system here. Now we're gonna see the change with the zeta. So if you don't know zeta, just take a look. It's a damping ratio. Now we're gonna see in MATLAB how we define this. Our second system, let's see. Let's say our time frame. Then we're gonna see our y function. Now we have zeros here. In our system 81. So now here 4. Say I equals to between 1 to 4. All right. So for our damping ratio, we're gonna see the change in zeta from 1 to 4. Now we define in here our numerator equals to parentheses, and we're gonna write here our a function we write, and we write your I, the change zeta change in the parentheses. All right. So the same with your denominator. Denominator will be EI and EI. All right. Forget the parentheses here. So now it's also okay. Your numerator, denominator, we define it. Now we need to define our Y. As you remember from the first experiment, we just define it with like this in our function, and then we're gonna put our step response again. In a step response, you just write your numerator, comma, denominator, and with respect to time. Yeah, so often we're gonna end our function again. Then we can start to plot again. So in here, we're gonna plot all of them with respect to zeta, but we're gonna label them. So how we're gonna do it, t comma y. So for the y, first value, first one. And now I'm gonna add comma here, and parentheses. So first I want to see their step response in O, right? So I don't want a normal comma, actually normal graphic, so I want it to represent as O. And then now you can go to the second one. It's the same with the first one. Again, you write your T comma Y. Now we're gonna go to our second value. All right. And then you just add comma. So this one I want to represent with X. All right, you represent it with X for the second value. Now we'll go on at the same with T and Y. Then in here again, you're gonna write your third value, and I wanted to represent, like, let's say dash. Okay, one is enough. All right, again, I'm gonna write the Y function again with respect to time, comma, and our third value. Okay, it's fourth value. All right. Again, comma, and then you write your representation symbol, let's say a comma dot. So see the difference from the other one. Right, again, the last one, you write grid here for the plot, and then you label your X label, it's represent our time again here, T second, and Y label, our outputs again. Our outputs. All right. So now let's run this section for here now. Let's see, we missed something here, I guess. Miss anything? Oh, we missed a comma here. All right, so a comma can ruin your code again. Anything, a comma here again. Okay. Okay, so as you can see, we plot our zeta changes in function. One of them is represent with O, one of them is represent with X, the other with dash and dash comma. Yep. Yeah, so as you can see, you can represent it as with your labels here. We represent our zeta first value, it was O. This is our first value zeta. The others are going to 0. All right. Any question, guys? Is this one clear? How you represent your zeta changes? Zeta is your damping ratio. Your damping ratio, let's say it's changed from 1 to 4. And we want to plot this. Okay, let's go to our last one. Let's clear our values. So our last experiment, we're gonna obtain rise time, peak time, maximum overshot, and settling time. Let's define our system again. Nominator, -25. Denominator 1, 6, 5, 6. Okay. So our time frame, you're gonna pin your time frame again. So now I wanna see change this time with 0.005 plus our settling time has a plus and minus 0.5 percentage change. So we need to see the changes. That's why we define it. And then let's go to our function now. Y comma t comma x comma t. So in here, we're gonna plot a step response again, our numerator and denominator with respect to time again. So here, I would just wanna plot it first, right? When you just need to write time and your function, and your grid, of course. You can your X label here. It was, let's say, time, say t sec. All right, for Y label, Y label will be our output again. Output, let's say YT. All right. So here, now we're gonna calculate the rise time, peak time, overshot value. So here, let's say R is 1, Y. Line. Here, in a Y function, we add our R, we define R, and then say it's smaller than our input is a unit step input, so it's 1, our unit step input. So we're gonna define it as 0.1 respect to time. You get your comma, and R here is equals to R plus 1. We need to return value. Then end this function. Yeah. Now we're gonna write the formula for the rise time, peak time, and overshot value. Saying Y max first here. We need to write this in parentheses. Yeah. So here we need the maximum Y values and maximum time values in a Y function to calculate our overtime, rise time, peak time, and maximum overshot. By this function, you can get them. So then now we're going to use them in formula. Let's say peak time, right? Let's say peak time. We can define it as equals to. Now we need to write our function. Right? TP maximum time minus 1. So it will just our minus 1 is come from the our input function is step unit step function. That's why we add minus 1 for the peak time. TP your maximum time minus 1, and then you are gonna multiply it by 0.005. Yeah, right. So we define our time frame here with this, and then go to the next one. Next one, let's say which one, max overshot. Right. overshot is just here we get y max value defined in the function, so we just get the maximum. Overshot is our maximum value. Now I'm going to show it in a graphic also. Say y max minus 1. Our maximum value in a function, and minus 1 is come from unit step function. You subtract it from your input function, and you will find the overshot value. Okay, and define our S here. Okay, 98 and okay. And let's say it's from 0.91 to 1. Let's say 0.2. Now it's minus 1. So here we're going to define S value between 0.98 to 1.2 for finding our settling time. Settling time, we talked about settling time previous week. What was the settling time, guys? Do you remember? Find the settling time. We talked about settling time previous week. You should have remembered it. What was it? 0.005 or change in time. So this is the formulas for the settling time, for max overshot, peak time, and anything we forget, the rise time, peak time, overshot. Yeah, we didn't write rise time, I guess. Yeah, let's define our rise time here. Rise time, for the rise time, our formula was r minus 1 times, again, our time frame 0.005. Yep, okay. Now let's run our sanction. Okay, as you can see, we define our rise time. You know what the rise time is? We define the rise time as the time it takes to get from 10% to 90% of steady state value of a step response, right? For this function, steady state response is somewhere between here, right? 1.1 to 0.9. So rise time is defined get from 10% to 90%, right? 90% is here. So the time takes to from 10% to 90% will be our rise time. It is around here, right? Let's say 10% here and 90% here. So the time will be something 0.5. Yeah, we define it as 0.55. And our peak time is the time takes that our system get a peak value. It's 0.70. See, our peak value, it's at the 0.78 time. And overshot, maximum overshot is the system response to our overshot our steady state, right? Our steady state is here, but our system response higher than that. We call this overshot, and overshot value is 0.009 here. Like our steady state is around here, 1.1, let's say, and its overshot will be 0.001. And settling time. So we talk about it from previous lab. You should remember it. Anyone want to explain settling time? You will get plus for the settling time. Anyone? No Google it. Okay, don't Google it. You have 5 seconds. Okay, no one. Let's say, okay. Our settling time is our system, how much time it takes for our system to go to the steady state, right? Steady state is it's around 1.1 here. See the system where it's stable, right? We have a average around 5% minus plus in a range. It can goes up and down, minus plus or 5. If in MATLAB, its steady state is 2%, it can go up or down. So settling time is the time take for a system to go to the steady state. It's here. Our system is steady around here, right? Somewhere here. It goes to the steady state. So it's around 1.18 calculated here. Okay, guys, any question till here? What is rise time? What is peak time? Overshot, settling time? All clear? Are you guys here? Wait. No questions. That's not good. You should have questions. Okay, then you understand very well. Okay. Okay, we're gonna upload an homework with Nejat Hoca. And for the next week, I'm thinking about the settling time is not constant. Of course, yeah, every system is different, so settling time is different for all systems. Settling time is the time takes for a system to go to the steady state. For this system, it takes around here, like around here, it enters the steady state space and goes to infinity. So for this system, it's 1.18 we calculated, and it will be different for other systems. Yeah, for the next week, just take a look again this for this lab. I'm gonna ask about the rise time, peak time, overshot. For this lab, I want you guys to create a system and find their rise time, peak time, and settling times and overshot. All right, take a look at this function, and I'm thinking about a little quiz for the next week. Okay, guys, any question? Okay, guys, that's all for today, and see you next week. Have a nice day, guys.